Thanks to Allah subhanahu wa ta'ala for all his blessings and bounties that he has bestowed upon us. فَبِأَيِّ آلَاءِ رَبِّكُمَا تُكَذِّبَانِ? Which of the blessings of your Lord will you both, jinn and insan, deny? We need to make shukr to Allah subhanahu wa ta'ala who has created us as a mankind, the best of all the creations, the ashraful makhlukat. So we need to think and ponder why Allah subhanahu wa ta'ala has given each one of us an existence, the real purpose, the objective of our life. Allah subhanahu wa ta'ala states in the Holy Quran, وَمَا خَلَقْتُ الْجِنَّ وَالْإِنسَ إِلَّا لِيَعْبُدُونَ. More or less meaning, I have created the mankind and the jinn only for my worship. How to worship to Allah subhanahu wa ta'ala? He's been very, very kind, very, very merciful by sending Anbiya alayhi Islam to guide the humanity so that each and every mankind could be successful, not only in this life but the life hereafter. So in order to get the real success, we need to follow the commandments of Allah subhanahu wa ta'ala, the way shown by the Prophet sallallahu alaihi wasallam. So inshallah, learning, talking and propagating it will be very, very beneficial for all of us. Today is 23rd of December, and we are going to take into consideration one of the vital topic of this course. We started off with the idea, with an overview of limit, continuity, and then differentiation with few practical implications by taking into consideration applications. Now we are interested to go in the reverse direction, the other way around, antiderivative. In the previous section, we concerned ourselves with finding derivatives of functions and their applications. One natural question: given a derivative, can we recover the original function back? So based upon this idea, we got a derivative. Now we are interested to go back to the original function. Are there any chances to recover the original function? If the answer is yes, is it gonna be 1? So another technical argument is there. So to some extent, we can recover the original function. And in this section, we are going to introduce the idea of anti-differentiation and integrals. So in the next few lectures, we will work through some basic techniques on how to recover antiderivatives, and eventually you will see more physical interpretation of integration when we discuss definite integrals. So the starting point, for example, we take into consideration 2x squared plus 4, and we are interested to compute its derivative. Pretty simple, it will return you to 4 times x. And now just imagine, instead of 4, if we have 5, will it make any difference to the outcome? If there is 3, if there is 1, if there is 0, for example, or minus 1, minus 2, minus 3, will it make any difference to the outcome? So we say that the outcome will remain the same, 4x every time, whatever the constant is there, together with this variable term. So 4x is the outcome by taking the rate of change of this expression with respect to x. Now from 4x, if you assume behind the scene, if you label this expression as f of x, then derivative to f of x is equal to 4x. 4x is at our disposal, f prime of x. F prime stands for rate of change of f with respect to x. So we got 4x as the outcome in terms of rate of change. How would we find the original function? We are interested to go back. And is there only one with this derivative? We have seen that if you change 4 by 5, if you change 4 by 3, if you change 4 by 0, minus 1, minus 2, the outcome is going to be 4x every time. So when you go back from 4x by taking antiderivative, and we are interested to return back to the original function, are there any chances we can recover the original function? Something like that. If the answer is yes, is there only one with this derivative? I will say that no, there are chances. One possibility that 2x square plus 4 as an outcome, 2x square plus 5 is another possibility, 2x square plus 9, for example. So finally, many options are there. So this is all. When you go back from the derivative to the original function, we will be having constant known as constant of integration. It's an arbitrary value. C could be 4, C could be 5, C could be 9, minus 1, minus 2, and then so on. So this is all. Whenever we perform integration, we reverse the process of differentiation. There will be constant of integration. Now, what is the definition? If you look into the definition of antiderivative, we say that a function capital F is said to be an antiderivative of small f on a given interval I if derivative to f is equal to f of x. So again, capital F is said to be antiderivative of small f if this condition is satisfied. So the definition is there. So f obtained from this relation, how will you get it? By taking an antiderivative. So once you take the antiderivative, later on we will look into that. The derivative will cancel out and we will be having f as a result of that. So we say that f is going to be antiderivative of f if this condition is satisfied, because antiderivative is on top of derivative. So there must be a foundation behind the scene. The foundation is derivative. If you have got something at your disposal in the form of derivative, so we can perform antiderivative. So if f prime of x is equal to small f of x, so antiderivative to this one will result in the form of f. To the right hand side, the expression would be there, the integral of f, of course. So as a remark, be aware that not all functions have an antiderivative, but when they do, a general technique called as integration gives an antiderivative. Just like if you remember from the overview of differentiation, we take start from differential. Then we talk about average change and finally instantaneous rate of change to describe derivative. The process of finding derivatives of a function is known as differentiation. So pretty much on the same line, the process of finding integrals, finding antiderivatives is known as integration. The technique to find antiderivative is known as integration. Let f of x be an antiderivative. Symbolically, we label it capital F be an antiderivative of small f of x. Then the expression, this one, is known as indefinite integral. What we see from here, from the definition, capital F is to be regarded as antiderivative to small f. If this condition is satisfied, f prime of x is equal to f, so then behind the scene capital F is going to be antiderivative of f. So for example, we take start now with labeling capital F to be an antiderivative of small f, then the expression f of x plus c is going to be described as indefinite integral. It's an integral, but without any definite value, without any certain value. Why is that? Because of c. C belongs to the set of real numbers. So in that set of real numbers, we have in finally many options. So this is how we say that indefinite because of the arbitrary constant, and we know the idea. Why do we need to introduce the constant of integration from here? Antiderivative is on top of derivatives. So when you look into the derivative, how do you manage those constant terms? Because of infinitely many options behind the scenes. So this is all. When we talk about antiderivative, we will be having arbitrary constant c. Integral sign is there. F of x is known as integrand. X is a variable of integration, and c is going to be the constant of integration, arbitrary constant. So it's an indefinite integral. But if you plug in the limits later on, we will describe the geometrical interpretation. Geometrically, it is going to describe area under the curve. The curve is going to be described by the expression y is equal to f of x. So there should be some boundaries over there. So boundaries are going to be tackled by those values of the variable of integration, I to b. So this is how the definite integral is going to be described. So the difference between indefinite and definite is that there won't be any constant of integration while talking about definite integral. There will be definite value, certain values there, unique values there. Over there is no certainty. Indefinite values are there. So this is how it is known as indefinite integral. So pretty much the same idea. You initially introduce the constant of integration, f of x plus c. But because once you apply the upper limit and the lower limit, c is going to be cancelled out and we're left with certain value. F of b minus f of a is a value of definite integral. What is a? Is going to be the lower limit. B is going to be the upper limit. Basically, they are the values of x, the lower and the upper limit. So eventually, they are going to describe the boundaries. Boundaries for a certain area under that particular curve, bounded from the left-hand side, from the right-hand side by x equal to a and x equal to b. When you take x equal to a, it's a straight line parallel to y-axis, another straight line, x is equal to b, parallel to y-axis. Generally, b is going to be greater than a in this case. So what if you look into the essential components to describe a definite integral? So have a look. We need to go on the sideways board. So we will be having integral sign. The limits are there. F of x is there, and dx, differential of x. So we see that this whole thing is going to be integral. Integral of f What are the components we have? Integral sign is there. One of the essential component. A is going to be the lower limit. B is going to be described as the upper limit. What is F? Is going to be described as integrand, the one which is going to be integrated. And X is going to be described as variable of integration. So these are the essential components to describe integral of F from A to B. So effectively, these are the values to the variable of integration, x equal to A, x equal to B, but we hardly place in x over there because it is understandable that these are the limits for the variable of integration. The variable of integration is going to be x in this case. So with all these ingredients, with all these essential components, we say that this whole thing is going to be integral of f from A to B. And since the limits are there, so we say that surely it will take you to a definite value, certain value as an outcome. So definite integral is going to be there. Essential components, there must be integral sign, there must be lower limit, upper limit, the function over there to be integrated, and variable of integration. So this is how we will be having an integral of a function to be integrated with respect to variable of integration together with the limits of integration or the values, the boundaries for the variable x being lower and upper limits. The technique to find the antiderivative of a function is known as integration. Derivative to integral. So, of course, we know that once you take a derivative of a function, then the antiderivative will kill the effect and you get the original function back pretty much on the same line. If you have an integral and you are interested to get the original function back, so kill the effect by taking derivative. So pretty simple idea is there when we talk about differentiation and integration. Remember differentiation, for example, you got a quantity at your disposal and you cut it down into small pieces. This process is known as differentiation. We subdivide into small pieces. And then as a reverse of that, the reverse process of that, combine together all those small pieces as one unit. So differentiation to cut it down into small pieces. And the reverse process of that combined together as one unit is known as integration. We integrate, we unite together as one unit. And from the previous topic, the fundamental definition of derivative, plenty of ways we can describe derivative in terms of h, in terms of x approaches to c, in terms of an increment delta x. So plenty of ways we can describe. the fundamental definition of derivative, f prime of x. So we got an idea about the antiderivative. So how do you look into the antiderivatives? Plenty of techniques are there. Plenty of techniques are there. Of course, we are not going to go with them in detail. Rather, we will try to take a glimpse of idea, because it is assumed that you must have gone through with them extensively in the previous classes. So we try to take a glimpse of idea with those techniques by taking simple examples. The very first technique is known as basic substitution. So we need to substitute something to make things simple. For example, in this case, you have to be smart enough to take this expression 8x squared plus 1 and replace it by an arbitrary parameter like t, for example. Since variable is to be changed, so dx, differential of x, should also be changed. How do you get? It will be obtained from this substitution, 8x squared plus 1 to be replaced by t. So dx should be obtained from here. How do you get it? 16x squared dx would be equal to dt. Taking differential to the left hand side, to the right hand side. So luckily, this expression, the numerator together with the dx is equal to dt. Otherwise, we were interested to take an expression for dx only. But over here, luckily, this whole thing is to be replaced by dt. Now, by replacing 8x squared plus 1 equal to t, and that expression by dt, so this whole thing is equivalent to that one, dt upon t raised to power 1 by 2. So quite simple expression is there. So you can bring this one in the numerator, the power is going to change its sign, so it is now with a negative sign. Utilizing the basic property, derivative to t is available, so increase the power by 1 and divide it by that power. So minus 1 by 2 plus 1, 1 by 2 divided by that power plus constant of integration, because it's an indefinite integral. There is no definite value, no limits are there. So this is how we will be having the constant of integration. So the answer is there. Simplify this one. So 2 times t raised to power 1 by 2. But this answer is in terms of variable t. The statement was given in terms of x. So by utilizing backward substitution, t to be replaced by 8x squared plus 1. So this is how the final answer is there. Initially, you see that things are a bit demanding, but if you make basic substitution, simple substitution is there, we have obtained pretty simple expression, and then we look for the integration. Sometime we also make a square over there to make things simple. For example, in this case, like x squared minus 2x plus 1. So the ideal scenario is that we make derivative of the denominator somewhere in the numerator, but you see that it's a variable, 2 times x being one of the component of the derivative, minus 2 to x minus 2. So you need to have variable over there, but we see that it's not there. So how do you look into the alternative option? So we say that if you complete the square, x squared minus 2x plus 1, now that 2 can be split into 2 pieces, 1 plus 1. There is no harm doing that. But by expressing 2 as 1 plus 1, now you see that the first 3 terms is a square to x minus 1. So it's a complete square, x minus 1 square. Second one could also be written as 1 square. So it is like 1 upon x square plus a square. A stands for 1 here in this case. So we know the formula. 1 upon a, tan inverse x upon a. So utilize that formula. Just recall from the previous classes, because many things you need to recall from the previous or assume knowledge. The formula is there for 1 upon x square plus a square. So 1 upon a tan inverse x. X means x minus 1. In this case, upon a means 1. It's a definite integral, so we have the upper limit, the lower limit, apply those limits, and eventually tan inverse of 0 is 0, tan inverse of 1 is going to be pi by 4. Simplify that, so eventually you have 2 pi as an outcome. Certain values there. Sometime we have trigonometric expressions, so we need to utilize trigonometric identities. Plenty of trigonometric identities are there in terms of sine, cosine, and secant, cosecant, cot. Those 6 trigonometric functions are there. So for example, secant x plus cot of x square is there. So very first thing is that break this square. Secant of square plus cot of square 2 times secant cot. Utilizing basic property of integral, separate integral to each of those 3 terms. Directly we can compute an integral to secant square. It is going to be tan because derivative to tan is secant of square x. So as a reverse process of that, integral to secant will return you tan. Cot of square by utilizing trigonometric identity could also be replaced in terms of cosecant. So cosecant square x minus 1. And from the last integral, secant is basically the reciprocal to cosine. So 1 upon cosine, cot is the fraction between cosine and sine. So cosine will balance out and we left with 1 upon sine. So 1 upon sine is cosecant. And then we have direct formula for cosecant. In fact, there are more than one formula. So one of the formula is there, log of cosecant x minus cot of x. So integral to cosecant square x is going to be cot with negative sign. Minus x is there because it's integration with respect to variable x. So this is how you will be having an expression. It's indefinite integral, so there must be constant of integration c. Improper fraction. The difference between proper and improper fraction is that if the degree of the polynomial in the numerator is greater than or equal to the degree of the polynomial in the denominator, we say that the fraction is going to be improper fraction. You see that the degree of the polynomial in the numerator is going to be 2, whereas the degree of the polynomial in the denominator is 1. So 2 is greater than 1. So if something like the degree of the polynomial in the numerator is greater than or equal to the degree of the polynomial in the denominator, we say that the fraction between these 2 polynomials is known as improper fraction. So first of all, you need to reduce. First of all, you need to convert into the corresponding proper fraction. Proper with the degree of the polynomial in the numerator must be smaller than the degree of the polynomial in the denominator. How do you do that? Simple in division is there. You need to bring the concept of division. So from the previous classes, as an assumed knowledge, when you perform division, what are the essential components? Again, there must be divisor. Divisor is going to be 2x plus 3. Divisible, the one which is going to be divided. It is known as divisible. In this case, divisible is 4x square minus 7. Divisor is 2x plus 3. So once you divide 4x square minus 7 plus by 2x plus 3, there will be quotient. Quotient means the answer. Simply in the loose term, we can say that. And there will be something left over known as remainder. So there are 4 components. Divisor, in this case 2x plus 3, divisible, 4x square minus 7. So as a result of this division, there will be quotient. Quotient means the answer. So the answer would be this one, 2x minus 3. And the leftover, in this case, the leftover is going to be 2, remainder. So this improper fraction would be written as quotient plus remainder upon divisor. So every improper fraction would be expressed in that particular fashion. Quotient plus remainder upon divisor. Now you see that if you look into this fraction, it's a proper fraction. 2, you could take it like 2x raised to power 0, for example. So 0th degree polynomial and first degree polynomial. So 0 is smaller than 1. Degree of the polynomial in the numerator is smaller than the degree of the polynomial in the denominator. So we say that yes, it is going to be a proper fraction. So separate the integral for 2x minus 3 and that proper fraction. Now we can look into the integration. Simple integration is there, minus 3x. And now you see that derivative of the denominator is available. So it will return you in the form of natural log. Apply the upper and lower limits. Simple calculation is there, and eventually you will be having a certain value, minus 4 plus natural log of 9. So if there is an improper fraction, first of all, you need to reduce, you need to convert into the corresponding proper fraction. So how do you write it down? Quotient plus remainder upon divisor. From this fraction, divisible is there and divisor is there. Resultant in the form of proper fraction. Sometimes you have more than one terms in the numerator, so better off to separate them. So in the numerator, we have 1 minus x, for example. Okay. So you see that we have more than one terms in the numerator with combined denominator. So we split them into two pieces. So one piece with that numerator 1, the other one with that variable x. So separate them. So this is known as separating fractions. So we have now two fractions over there, 1 upon 1 minus x squared, x upon 1 minus x squared. So one of the best option is there, once we have a fraction, to make the derivative available in the numerator for that denominator. So you see that if you take this thing, 1 minus x squared, you can also take into consideration the option of backwards, the basic substitution. But anyway, now we are mature enough, directly we can look into the derivative of this denominator. I mean, the expression is that one inside that radical sign 1 minus x squared. Derivative to that expression is minus 2x. So x is available. You can take this negative sign inside this integral sign. So minus x effectively is available. So multiply and divide by 2. So this is all. You will be having derivative in the numerator. Once you have derivative of this thing in the numerator, so we can apply the formula. I mean, you can also bring this one in the numerator, and then the derivative would be there. So increase the power by 1 divided by that power. Simplify that. Eventually, it is going to be that expression. For the first one, it's a direct formula. Sine inverse of x upon a is going to be 1 in this case. So simply we say that it is basically sine inverse of x. Indefinite integral is there, no limits are there. So this is we will be having constant of integration. Now, if you omit constant of integration over there, this is not going to be the answer because we are expecting to have indefinite values. So constant of integration should be there as an essential component of the answer because there is no certain value. If there is no C, it means that the answer is definite. Only one option is there. But we see that If there are no limits, there will be infinitely many options, so the constant of integration should be there. 1 upon 1 plus sine of x. So we encounter with an expression something like that. So an alternative option is there other than basic substitution, trigonometric identities, improper fraction, completing square, separating fractions. We have an alternative option. 1 upon 1 plus sine. So what we do, basic idea is that we multiply and divide by that factor with opposite sign to the given sign. If you look into this expression, we have been given plus sign 1 plus sine of x. So we multiply this expression 1 and sine, but by changing the sign, if it is plus, we have to change into minus. If it is minus sign, so we need to change it to plus sign. So we multiply and divide by that factor by changing this sign. So in other words, multiply and divide by 1 minus sine of x. So 1 minus sine of x upon 1 minus sine of x, yes, we can do that. It's basically message is that you multiply this whole thing by 1. There is no harm doing that. So this is how we say that multiplying by a form of 1. So this whole thing is identical to that thing. So resultant and the form of 1. So this is how we say that effectively it is 1. But anyway, by doing so, we have an expression which can be computed easily. Like numerator is a multiplied by 1. And denominator 1 plus sine x times 1 minus sine of x. So you need to bring the simple formula a plus b into a minus b. So resulting a square minus b square. And then use trigonometric identity 1 minus sine of square x is equal to cosine of square x. Same numerator. And then split into two pieces, separating fractions 1 upon cosine square, sine upon cosine of square. 1 upon cosine of square could be expressed in terms of secant of square because it's a reciprocal to secant. Sine upon cosine is going to be tan. 1 upon cosine is secant. So we express in this way so that we will be having integral. Because secant times tan is derivative to secant. So this expression tan into secant will be integral to secant. Secant of square x is basically derivative to tan. So integral to secant of square x will be tan of x. So you need to recall basic formulas. Secant of square x, integral to that is going to be tan. Integral to secant times tan is going to be secant. Plus constant of integration because it is going to be indefinite integral. Eliminating square roots. You see that we have only one expression, 1 minus cosine of 2x. There is no helping term over there. There is no helping factor over there. So only you need to play around with this expression. So what we do, we utilize half angle identity. 1 minus cosine of 2x is basically 2 times sine of square x. Angle is going to be half, 2 times x to 1 times x. So 1 minus cosine of 2x is basically 2 times sine of square x. So 2 with that radical sign is taken outside the integral, and sine of square x inside this radical sign will result in the form of sine of x only. So this is all. If you eliminate this square root, this radical sign, so you will be having simple expression. But how you do that? By utilizing half angle identity. So sine, we know that the integral is going to be minus cosine. Because derivative to cosine is minus sine, so there must be a negative sign. So, or you can take it over here. Apply the upper and lower limit. So minus 1 is there. 1 is there, but because of this negative sign, combine them. So eventually it is going to be 2 times square root of 2, definite value, because it's a definite integral. with lower and upper limits are available. Mixture of many things over there. Assorted integration, miscellaneous. Cosine of theta times cosecant of sine of theta. The variable of integration is going to be theta. So we are interested to make this expression as simple as possible. So what we do, we initially try to fix this one. So it's an angle to cosecant sine of theta, though theta is going to be an angle to sine, but inside this bracket it is going to play the role of angle to cosecant. So why not substitute this one, sine of theta. So we take sine of theta equal to x, for example, introduce a dummy variable, and then since we are going to change this variable of integration in terms of x, so d theta should also be changed. So taking differential on both sides, so cosine of theta times d theta to the right hand side, differential of x is going to be d theta, dx to the right hand side, to the left hand side, cosine of theta d theta. And sometime you are lucky to have this expression, like you see that in this case, cosine of theta together with d theta is going to be replaced by dx once you replace sine of theta by x. So make this substitution. So sine of theta to be replaced by x, so it will be cosecant x. And this combination, cosine of theta times d theta, will be replaced by dx. So we will be having cosecant x dx. Now you can look into the integral of cosecant. It's a matter of finding an integral to one single factor cosecant x, utilizing the formula, basic formula. So integral to cosecant x will be natural log, one of the form of the formula is a natural log of cosecant x minus cot of x plus constant of integration, because it's indefinite integral. So the answer is in terms of x, but we know that the answer has to be in terms of theta. So by backward substitution, x to be replaced by sine of theta. So replace it over here, over here. So this is all, the answer is there. So we make substitution to have a simplified expression as much as possible so that we can directly look into the outcome. So once you get the outcome, utilize backward substitution to get the answer to the given expression. The given expression is in terms of theta, so the answer should be in terms of theta. Integration by parts. One of the most famous component of integration. So integration by parts. So you need to bring the formula. So what the formula is there? Normally we regard them u into v form. I mean, if you label this one as u x cube and you label this one e raised to power x by v, so it is going to be like u times v. So what the formula, I mean, just to memorize this one, u as it is, integral of v, we know that the integral of e raised to power x is going to be e raised to power x minus integral of integral to v times the derivative of u. So integral of e raised to power x is e raised to power x times derivative to x cube 3xk dx. So this is how the formula is there. If you memorize in terms of u into v form, so label it u, for example, in this case x cube, v the second one. So this is how the formula is going to be implemented. Again, you need to apply the same formula. 3 can be taken outside the integral. So now u is going to be x square, v is going to be e raised to power x. Apply the same formula. Derivative to u means derivative to x square. And finally, derivative to x is going to be 1. And once you have 1 over there, so it means that you just integrate e raised to power x. So it will result in the form of minus 6x as second to last term, because the last term should be constant of integration. So this is how the answer is there. Because one of the most frequent component of integration is known as integration by parts. One of the most frequent technique. Over and over, we implement this one, integration by parts. So one of the most prominent one. So we see that, okay, we need to perform once, twice, thrice, 4 times. 4 times you need to perform integration, and then you have the answer. There is an alternative way, because this is going to be the most prominent technique being utilized frequently. So we have an alternative option. An alternative option to integration by parts is known as tabular integration. So from the label tabular, so means we are expecting to have some sort of table behind the scene. So how you do that? We take a glimpse of idea. We have seen that in the technique known as integration by parts, we need to perform 4 times the integration, and then the answer is there. And now we see that what is the alternative option? Alternative to integration by parts. So it is known as tabular integration. So we need to go on the sideways board to take a glimpse of idea of this technique known as tabular integration. What is tabular integration? So we have to integrate this one x cube e raised to power x. So what we do, we label them just like in the technique of integration by parts. We memorize the formula in terms of u into v. We say that uv form. So we label it as f, and the second one as g. Basically, f of x is there, surely, and g of x is there. So what we do, you need to make a sort of table. What the table is there, in the first column f of x and its derivative. You need to compute in the first column of the table f of x. You label it x cube as f of x. So f of x and its derivatives. In the second column, you need to list down g of x and its integrals. What is g of x? We have labeled as e raised to power x as g. So take its first derivative, so it will be 3x squared. Second derivative, 6 times x. Third derivative, 6. And then 0. Of course, the next derivative to the constant value with 6 is going to be 0. To the other end, integral of e raised to power x, e raised to power x, integral to e raised to power x, integral to e raised to power x, integral to e raised to power x. So combine them. F with an integral of g. First derivative of f with the second integral of g. Second derivative of f with third integral of g. And then so on. So resultant is going to be, for example, if there is e raised to power x, they are all going to be 0. You need to combine them with alternative sign, plus, minus, plus, minus, plus. Combine them. So the first combination, or the first term of the answer, would be the combination of x cubed with e raised to power x with positive sign. So this integral would be equal to, so the first term of the answer would be x cube x cube times e raised to power x with positive sign. Then the next combination 3x squared times e raised to power x with a negative sign. Next term would be the combination of 6x and e raised to power x with plus sign. Next term with the negative sign minus 6 times e raised to power x plus 0 time, and all those terms are going to be 0 because 0, 0, 0, 0. Derivative to 0 is 0, 0, 0. Multiple of anything is going to be 0. Since it's indefinite integral, there must be a constant of integration c. So this is the inside one line. You can get the answer as an alternative option to integration by parts, known as tabular integration. Pretty simple technique is it? Very elegant. But there are some measures that you need to take before you look into that. Is it viable to each one of the expression, whatever the expression is there, means the product of exponential with trigonometric, product of exponential with the logarithmic function is there? So the answer is no. It has some limitations. What are the limitations? Number one, need to have f of x. So f of x is such that whose derivatives come to 0 eventually. So you see that in this case, yes, f of x, ideally it is going to be x cube, because eventually the derivative of x cube is going to be 0. The first one is 3xk, second one 6x, third one 6, and then the fourth derivative is going to be 0. So we need to have f whose derivatives come to 0 eventually. So it is not going to be valid for trigonometric functions like sine of x times e raised to power x, cosine of x times e raised to power x. And the second limitation is that we can't swap them. We can't exchange f and g. I mean, you can make e raised to power x to be f and x cube to be g. What we do in the table, we list down f and its derivatives in the first column and g and its integrals in the second column. So you see that if you take e raised to power x, label it as f. So f and its derivatives, it's a never-ending process. E raised to power x, e raised to power x, e raised to power x infinitely many times. And if you label x cube as g, then the integral of x cube is going to be in terms of x4. Integral of x4 will result in the form of x raised to power 5 and then so on. So the power of x is going to be increased with the passage of time. So it's a never-ending process. So the ideal case is there when you have a product of polynomial together with trigonometric function, polynomial together with exponential function. So that polynomial term to be labeled as f, because that's what is the requirement. Need to have f whose derivatives come to 0. So this is one of the best options, the tabular integration. In case if you have an expression like polynomial term together with exponential term, polynomial term together with trigonometric, so that polynomial term should be labeled as f. Very elegant alternative option is there. Integration of rational function by partial fraction. So once we have a rational function. So rational function means just like a rational number is there, we got a fraction. So if you have a function expressed in the form of p upon q, p of x upon q of x, so we need to look into this technique known as integration of rational functions by partial fraction. So we are going to split into partial fractions. Depends upon the number of factors are there. So the very first thing is there for the rational function. Remember, normally we take the rational function as a fraction of p upon x upon q of x. So f of x, for example, is given as p of x upon q of x. So what we do, very first thing, factorize the denominator. So very first thing that you need to do, factorize the denominator. No, chances are there those factors are linear and non-repeated in the denominator. Chances are there the factors in the denominator are linear but repeated. Chances are there factors in the denominator are quadratic, non-repeated, or quadratic and repeated. So this is all the possibilities are there. So based upon those possibilities, we have the corresponding partial fractions. So take one by one. For example, we say that once you make the factors of the denominator, and we have non-repeated linear factors in the denominator, then to each non-repeated linear factor in the denominator of this form, so this is the linear factor, ax plus b, arbitrary values to a and b, for example, whatever it is, like x minus 1, 2x plus 1, so these are linear factors. There corresponds a partial fraction of this form, capital A upon ax plus b. A and b, small a, small b, they are known values, remember. That capital A is a constant unknown value to be determined. So the first possibility, to each non-repeated linear factor in the denominator, the corresponding partial fraction would be of this form, a upon ax plus b, where a has to be calculated, a has to be obtained, capital A. Now, if there are repeated linear factors in the denominator, like ax plus b raised to power 2, like ax plus b raised to power 3, 4, 5. So n should be at least 2 to have the repetition. So this is only possible if you have at least 2 times. This factor is going to be repeated, ax plus b times ax plus b, ax plus b. So n should be at least 2, 2, 3, 4, 5, and then so on. So there corresponds the sum of n partial fractions of the form. So as many partial fractions are there as the power of n. So if there are 2, for example, if n is equal to 2, there will be sum of 2 partial fractions. Corresponding to 1, it is going to be of this form, a upon ax plus b. No, since we have more than 1, so how you do that? A1 upon ax plus b plus second time a1 upon ax plus b square plus third term, if n is equal to 3, it would be a3 upon a plus ax plus b raised to power 3, and then so on up to the nth partial sum, partial fraction. Nth partial fraction is going to be that one, where a1, a2 up to an are constants to be determined. So non-repeated linear factor individually, a, and if you have another one, b, c, but if you have repetition over there, so you can label them like a1, a2, a3, a4. Independent, non-repeated linear factors. So corresponding to one of the factor, this one, corresponding to the second factor, it would be like b upon that second factor and c upon the third factor, and then so on. Now we have repetition in one factor. One factor is repeated over and over again. So you will be having the sum of as many partial fractions as the power of one factor is there. As many times one linear factor is repeated. So we will be having as many partial fractions over there. Third possibility basically, but fourth argument, to each non-repeated irreducible quadratic factor. Because if it is reducible, so you need to reduce it into the linear form, linear factor, repeated or non-repeated form. So we say that non-repeated irreducible quadratic factor in the denominator, there corresponds a partial fraction of this form. So this factor is irreducible, means we cannot further reduce into linear factor, and non-repeated. So we will be having two arbitrary constants or two constants to be determined, A and B. So the expression would be like this one, AX plus B. So this factor is there in the denominator. So this is how we will be having the partial fraction corresponding to each non-repeated irreducible quadratic factor. Rarely we have a chance of repetition in the quadratic factor, but if it is there, quadratic factor and it is repeated. So again, the same idea like in that argument, it is going to be the sum of n partial fractions of this form, a1x plus b1. Then to the first repetition, a2x plus b2. Second repetition, a3x plus b3 upon ax squared plus bx plus c raised to power 3, and then so on. Where a1, a2, a3 up to an, b1, b2, b3 up to bn are constants to be determined. So these are the procedures behind the scene. If you look into the theoretical aspect, so these are the options. But anyway, idea is that if you have cubic factor, for example, in the denominator, so then you can extend this idea pretty much on the same line. Ax squared plus bx plus c would be there in the numerator, and then so on. It's pretty hard to have cubic factor in the denominator, but anyway, if it is there, you can extend this theory. So we try to take a simple example. X plus 4 upon x squared plus 5x minus 6. So we see that we have a quadratic polynomial in the denominator. So we are expecting two values, means we are expecting two factors, linear factors. It's a simple case. So take this integrand, x plus 4 upon x squared plus 5x minus 6. So this denominator can be expressed in the form of two linear factors, x plus 6 times x minus 1. So you see that very first step is that factorize the denominator. Once you factorize the denominator, we see that we will be having two linear factors, non-repeated linear factors. So corresponding to x plus 6, it will be a upon x plus 6. Corresponding to that x minus 1, it will be b upon x minus 1. To each non-repeated linear factor, it will be something like a upon that non-repeated linear factor plus second one. So if you have two, like in this case, so it will be the sum of those two partial fractions corresponding to this factor, that factor, we will be having this one. So we are interested to find a and b. Since this thing is equal to that one, I mean, eventually, of course, is equal to this one, and partway through the journey, it is going to be basically the factors of the denominator. If you multiply both sides by this thing or by that thing, it will result you in this case, like this expression. Combine the terms in a way to the coefficients of x and then the constant term. Now you see you have x plus 4 to the left hand side and a plus b times x plus this constant to the right hand side. Since they are equal, so it is only possible if they have equal corresponding coefficients, coefficient of x and then the constant term, equate them. So equate this constant term, I mean this is equality sign means that they are equal to each other. So this constant term should be equal to that constant term. This coefficient of x should be equal to the coefficient of x to the left hand side. To the left hand side is 1, to the right hand side if it's a plus b. So equate them, the coefficients of the respective terms, a plus b is equal to 1. From the second one, minus a plus 6b, constant term, to the right, to the left hand side, constant term is 4. So now you have two simple algebraic equations. Two unknowns, a and b, two equations are there. So we are expecting to have unique solution. Whatever the technique that you apply, get the values of a and b. So this is how we will have it. So I take your attendance in the meanwhile. Yes, it's there. All right, so this is all. We will be having the corresponding values to A and B. So this expression has been reduced into sum of two fractions. So integral to this one will be the integral to this right hand side, just integrating. It's a simple expression now, x plus 6, derivative is a 1. So 2 by 7 can be taken outside, natural log of this one, 5 by 7 times natural log of this one, plus constant of integration. Further, you can simplify this one if you are interested to bring together as one unit these two log terms. So by utilizing the property, bring it as a power to this expression, bring that one as a power to this expression, and then combine them. So it will be as one unit, the most simplified form. So repeated linear fraction, you can look into this one. So you see that it will be square in the denominator, x plus 1 square. So x plus 1 as a linear factor, it is going to be repeated 2 times. An example for irreducible quadratic fraction, you see that it's a linear factor corresponding to this one. It will be a upon x plus 1. It's a quadratic one. So plus bx plus c upon x square plus 1. Rational fractions to partial fractions. I mean, if you make substitution like e raised to power t is equal to x, for example, then it will be x square 3x plus 2. Then you look into the corresponding partial fractions. Basic substitutions are there. Frequently we utilize them. Like if the expression is there a square plus x square, what do you do with x? Normally it is going to be replaced by a tan of theta. I mean, if you replace x by a tan of theta, it will be a square tan of square theta. By taking a square common, it will be 1 plus secant of square theta. A square minus x square. So if this is the form, either you replace x by a sine of theta or a cosine of theta, because in both cases the expression is going to be simplified. Like, for example, if you take this one, so a square minus a square sine of square theta, by taking a square common, it will be 1 minus sine of square theta, means equal to cosine of square theta. And then in the case of x square minus a square, so a square plus x square, and then a square minus x square or x square minus a square. So these are 3 possibilities. Mainly we look into that. So you need to put in the third case x by a secant of theta. Like in this example, 4 plus x square, it is just like a square plus x square. A is going to be 2. So you need to replace x by a, means 2 times tan of theta. And then this is all you need to apply. The substitution for the other components of the integral means you need to replace dx. You also need to replace upper and lower limits. So all of these things to be taken from this substitution. Dx will be obtained from this expression. Now, since these are the limits against x, since we are going to change the variable in terms of theta, so these limits are to be changed. Everything is to be obtained from this substitution. When x is equal to 2, for example, or when x is equal to minus 2 over there, what will be the corresponding value of theta? So take an example. When x is equal to 2, for example, so place it over here. 2 is equal to 2 times tan of theta. What will be the corresponding value of theta? So 2 will cancel out. You will be having 1 to the left hand side. So tan inverse of 1 is basically pi by 4. So once x is equal to 2, when x is equal to 2, the corresponding value of theta will be pi by 4. And when x equal to minus 2, it will be minus pi by 4. So since you are changing variable of integration, so differential as well as the limits should be changed. So replace all of them. So we say that this one is equivalent to that one. Dx is to be changed by this one, this expression. X over here by 2 times tan of theta, lower limit minus pi by 4 corresponding to the upper limit, it's pi by 4, and simplify this expression. So you see that it is much simplified. Simplified form is much easier to look into, and eventually the answer is going to be pi by 4. There are some reduction formula. We refer to the reference book if you are interested to see those formulas over there. Reduction formulas are there for sine and for cosine, and I mean directly you can look into the formula. For example, you are interested to look into the outcome for sine 7x, for example. What will be the formula? The reduction formulas are there in the reference book. So we recommend them in the reference book, all these formulas. You can try. What can be the options to be discussed as an example? So it's basically chapter number 8, techniques of integration, from reference book number 1. So all these techniques, it's not a new thing for you people because you have done all these examples expected in the previous classes at the intermediate level. So this is all we have gone through quickly with the techniques of integration. Like if you look into the first technique, basic substitution is there. So you need to utilize them. Integration by parts is there, and we have seen an alternative option over there. So integration by parts. So all these things, pretty simple. Idea is there. Trigonometric expressions are there. So we have tried to at least take a glimpse of idea, just to recall the basic concepts. Trigonometric substitutions, I mean, what should be an option over there? I mean, if the expression is there. So we have discussed all these options over there. Like the expression is a square plus x square, a square minus x square, or x square minus a square. So what should be the corresponding expression? So a secant of theta. So keep an eye on these things. You can look into those for practice purpose. And then we will be having partial fractions, rational function to be converted into the corresponding partial fractions. So based upon the factors in the denominator, we look into the corresponding things. So these are the techniques of integration you can try as a practice. All right, so we have plenty of things over there to be